Greetings, AP Statistics students. Today, we're going to do an activity that will get us into one of the fundamental ideas of statistics, hypothesis testing. So you may recall I mentioned that there was a woman, Joy Milne, who said that she could identify Parkinson's by smell. She noticed that her husband had developed a subtle musky odor. 6 years later, her husband was diagnosed with Parkinson's disease. And when she went into a room with Parkinson's patients, she noticed that those patients had the same subtle musky odor that her husband had. So the scientists were intrigued by Joy's claim, and they decided to design an experiment to test her ability to smell Parkinson's. She was presented with 12 different shirts, each worn by a different person, some of whom had Parkinson's and some of whom did not. The shirts were given to her in a random order, and she had to decide whether each shirt was worn by a Parkinson's patient or not. I'd like you to pause the video right now and answer the 3 questions on your handout. Let's take a look at the answers to these questions. Question 1. Why would it be important to know if someone can smell Parkinson's disease? Well, here, Joy noticed the smell 6 years earlier than the diagnosis. So early diagnosis would be very helpful. Question 2. How many correct decisions out of 12 would you expect Joy to make if she couldn't really smell Parkinson's and was just guessing? Well, if she was just guessing between one of 2 possible options, she would be right on average 50% of the time, or 6 times out of 12. And then finally, how many correct decisions out of 12 would it take to convince you that Joy really could smell Parkinson's? What if she got 7 right out of 12? Would that be enough? Or 8? Well, she actually got 11 right out of 12. So is that rare enough for us to be convinced that she really can smell Parkinson's? In other words, how likely is that to happen by chance alone? To investigate this, we're going to do a hypothesis test along with a simulation. So a hypothesis test consists of 2 parts, a null hypothesis and an alternative hypothesis. The null hypothesis is that there's nothing interesting going on. This is what we'd expect to see happen in the long run if she was only guessing, a 50% success rate. The proportion of correct identifications would be 50%. However, if Joy has the ability to identify Parkinson's, she should be right way more than 50% of the time. So the probability of success, or the proportion of successes here, will be greater than 50%. So we're only going to be convinced if we're far out in the tail of this distribution. Well, we're going to learn about something called a one-sample z-test in here, but as we're going to see next week, we've actually not met the conditions appropriate for this situation. So for now, we're going to do a simulation. You're going to get a set of 12 cards that represent the shirts that have been shuffled into a random order, and you're not going to turn them over. On the back of some of them are P's for Parkinson's, and others have NP for no Parkinson's. For each card, you're going to pick it up, smell it, and determine would that have been a shirt worn by a Parkinson's patient or a person that did not have Parkinson's. Once you've made your guess, you'll turn the card over and see if you're correct. You're going to repeat this for each card and record the number of correct identifications out of 12. Since our class is small, you're going to do this twice, and you want to be sure to shuffle your cards before you do it a second time. Here are the results from my 2 sets of simulations, and I started a dot plot here. You're going to create a dot plot in the front of the room once you're done with your 2 trials or 2 runs of your simulation. And I made a note over here as to where 11 occurred, which is what Joy got in her experiment. So go ahead, pause the video, and do your 2 sets of simulated 12 shirts. So in the actual experiment, I said that Joy identified 11 of the 12 shirts correctly. So she was correct about 92% of the time. Based on this small scale and the results we have on our dot plot, is it likely to get 11 or more shirts correct, assuming that the person was just guessing? In other words, 11 or 12 shirts correct, identified correctly by chance alone. So let's take a look at the results on the board. Did it happen at all? Did it happen only once? I'm guessing it didn't happen at all, and so our estimated p-value would be about 0. Pretty small. But of course, we only have, in this case, probably about 16 dots or 14 dots on our board in our dot plot. So what would be something we might do to improve our estimate of the true probability? If you said do some more simulated trials, your answer would be correct. However, we're not going to continue to shuffle index cards and smell the index cards. We're actually going to do a simulation using something called StatKey. So let's take a look at how we would do this with StatKey. I'd like you to actually pause the video right now and see if you can actually do all the items that are listed here in number 9. Let's go to StatKey and see if we can actually run the simulation. So I'm going to go to StatKey here. I'm going to change this to sampling distribution for proportion. I'm going to edit my proportion to be 50%, so 0.5. And I'm going to change this to be a sample size of 12. Let's just do one sample. So this time, Joy would have gotten 7 shirts out of 12. That's what the 0.583 is down here. 7 shirts out of 12, right, by guessing. Let's do another one. And another one. So we can see this is similar to the dot plot we had constructed in class. And notice here in the upper right-hand corner, it's a little hard for you to see, but it's showing you how many times we've run our simulation, and so on. Let's get up to 100 simulations. So 20, 30, 40, 50, 60, 70, 80, 90, 100, and then 1,000 simulations. And notice there were a few times here where we got results that were similar to what Joy had. Let's get up to 10,000 simulations. Notice that the center of our distribution is at 0.5, which makes sense since we edited the proportion to be 0.5. So let's see if we can identify the p-value. This is a right tail test. Since we're talking about our proportion being greater than 0.5, we need that to be greater than 0.5 to convince us. So let's see how likely it was to get these results by chance alone. I'll click on right tail here. And I don't know why that's not letting me change that number. Let me try this. Right tail. I don't know why it's not allowing me to do this right now. Hopefully it's working for you. There we go. Oh. This applet's not working. Oh, there we go. Let's change this. See if I can change this to be I want to change this number here, this 0.750 number, to be 0.91. There we go. I had to click on it. 0.91. And so I can see that it looks like there was one time when we got all of them correct, all 12 correct. But this happened 3 times or 30 times out of 10,000. So 30 times out of our 10,000 trials, we got results as extreme as what Joy observed, which was 11 out of 12 right in the experiment. So let's go back to the handout. So our simulated p-value was 0.0030, which is very unlikely to happen by chance alone. So if that's unlikely to happen by chance alone, right, assuming this is true, the probability of us seeing this is 0.0030. 30, which is more likely to be the truth? That the true population proportion is 50% or that it's more than 50%? Since this is unlikely, these results we saw were unlikely to happen by chance alone, this is the more likely outcome. And that's a little bit of reasoning that gets a little, it'll take a little bit of getting used to that reasoning, but I feel confident that you guys can handle that. So let's take a look at this here. It says an interesting note is that Joy's one mistake really wasn't a mistake. The shirt was worn by a person who supposedly didn't have Parkinson's, even though Joy claimed that she could smell the smell in the shirt. That person called the experimenters 8 months after the experiment and reported that he was just diagnosed with Parkinson's. So actually she was correct for all 12 shirts. So based on our simulation, the p-value would have been probably 0.0001, maybe one time out of 10,000. Something like this would happen by chance alone. Since it's unlikely to happen by chance alone, very unlikely to happen by chance alone, we can feel pretty confident that Joy actually has this ability to smell Parkinson's. One last thing for you to think about here is there a way to calculate this probability directly? Think about binomial distributions and see if you can calculate this probability correctly. Pause the video here for a moment. Did you try to calculate the probability? Well, to calculate the probability, we need to identify the number of trials, which in this case would be 12, the probability of success, which would be 0.5, and the number of successes, which would be 11 or more successes in 12 trials, so 11 or 12. Then you could use the binomial formula to do the calculation, or you could use your calculator. I'm going to use my calculator for this, and I'm going to enter my parameters for n, p, and x. I'll need to actually do two calculations and sum the results, the probability for 11 along with the probability for 12. That's under second distribution, binomial PDF. The number of trials is 12, the probability of success is 0.5, and the number of successes we're interested in is 11. I go down to paste, and actually I'm going to add the probability of there being 12 successes out of 12 when the probability of success is 0.5. So I just have to come down here and change this to a 12 and paste, and it's going to sum the two probabilities together. Our answer is 0.0032, which was pretty close to our simulated p-value from StatKey. Have a wonderful President's Day weekend, everyone.